Hello, Matthews. Gatos here. In this Chapter 5 lesson, we're going to be looking at applications of exponential growth and decay. So let's talk about growth first. So growth is something that is increasing. So we're going to have 100%, which just means all, plus whatever my growth rate is. This is my increase amount. And so when I add those together, I'm going to get a number that's bigger than 100%, which means my base will be bigger than 1. Remember, bases are always as decimals, not as percentages. Okay, then we could also have decay. So decay is 100%, which again is all of the amount, minus your decay rate, which is what you're going down by. So when I do 100% minus a number, I'm going to get a number smaller than 100%. So as a decimal, it's a number between 0 and 1. So, for example here, if we have a population of animals which is increasing, that means growing, in number by 7% each year. Well, we're going to take 100%, add to the 7% to get 107%, but we don't leave it as a percentage, we put it back as a decimal. The base is then 1.07. In the other one, I have the value of a tractor, which is depreciating, which means decreasing or going down by 15%. So that means it's 100% take away 15%, which is 85%. But again, we don't leave our base as a percentage. We put it as a decimal. So our base is 0.85. So in exponential form for word problems, y equals a times b to the t. Let's just break that down. Y is my final amount. A is my initial amount, how much I'm starting with. B is your base or your growth decay factor. So that's your multiplication factor to go from step to step. And t is some element of time. Okay, so let's try an example here. So we have a quantity of water and it has 500 grams of pollutants. Now each time water passes through a filter, 12% of the pollutants are removed. So since they're being removed, that means that I am decreasing, which means my base will be less than 1. So to figure out what the base is, it's going to be going down by 12%. So that's going to be 100% minus 12%, which is 88%, making my base as a decimal 0.88. A, of course, is my initial amount. That's how much I start with, which is 500. So putting that all together, my equation is going to be m equals a times b to the t, just like that. Okay, in the first question, I'm asked to determine to the nearest gram the mass of pollutants remaining after the water has passed through 4 filters. Now, those 4 filters are an x value. So that means x is given, y is needed. So putting that into the equation, I see that x is 4 here, and I have just a number. Y is equal to this number, 500 times 0.88 to the 4. So I can just put that straight into my calculator, and to the nearest gram, it would be 300 grams remaining after 4 filters. What about if I asked how many filters do we need to go through to reduce the mass to less than 150 grams? So 150 grams is a y value. So this is an example of y given, x needed. So in my equation, I'm going to replace y with 150. So to solve this equation, because x is my exponent, what I'm going to do is isolate my power and I'm going to use Bay. So divide both sides by 500. And then I have this number here. I'm going to put it as a fraction in lowest terms. So 150 over 500, put that as a fraction in lowest terms. Okay, so that's 3 over 10. So I'll have 3 over 10 equals 0.88 to the x. And then I'm going to use Bay, which just means put it back into log form. So base answer equals exponent. So putting that into my calculator, I can see that I get 9.4. So we want to figure out how many filters. You can't have 9.4 filters. So we have to ask ourselves, do I want to round it to 9 filters, or do I round it up to 10 filters? Well, to answer that question, I want to make sure that my pollutants are less than 150 grams. So what I'm going to do is look in my calculator to see what is the filters at 9, how much is left after 9 filters, how much is left after 10 filters, so I know how much I round to. So looking at this, I want to be less than 150. So here I'm more than 150, so it's not that one. This one here I'm less than. So it looks like I'm going to round up and say that 10 filters are needed. Okay, let's try another one. So we have students in a new college, and this college is growing at a rate of 4% a year. So if it's growing at 4%, my base is 100%, all of them, plus the extra 4%, which is 104%, as a decimal 1.04. Now, if the number of students continues to grow at this rate, its projected population will be 5,650 in 4 years. So we want to determine the current number of students at the college. Excuse me. So putting this into my formula, I have y equals a times b to the x. So this is an example here. I want it in 4 years of x given and y needed. Y being our A value. So this here, 5,650. Okay, so we have 5,650 in 4 years. Okay, so X is given, Y is given, and A is needed. So to solve for A, I'm just going to take the number that A is multiplied by and divide both sides by that. So dividing both sides by 1.04 to the X, I will get my A value. So plugging that into my calculator, I get 4,829.6. Now they want us to round it to the nearest 10 students. So if I were to skip count by tens all the way up here, I would get 4,820, 4,830. So those are to the nearest 10, and I can see that this number here is closer to this one here. So to the nearest 10, it would be that many students. Okay, so let's look at this question here. They've decided to expand the school, adding a capacity of 8,000 now, maximum capacity of 8,000. So they want to know, now that we know how many students we've started with, how long will it take to get to 8,000? So 8,000 students is the initial amount. Here's my growth rate to the n. We're trying to solve for n. So they take the log of both sides, totally fine. And then in this next one, it looks like they take the exponent of n and bring it down. And that's where they lost me. That's their mistake right there. Okay, so that exponent of n goes with 1.04, not with the whole thing. So you can't bring that exponent of n down. It only applies to the 1.04, not the entire thing. So what we need to do is apply the product law and then bring it down. So let's take that step and we'll do it again the correct way. So at this step here, this is what they should have done. So when you have logs that are multiplying the arguments, you can separate them into individual logs by adding. And now I can bring that exponent of n down. So I'm going to subtract the log of 4,830 from both sides. Bringing the n down, I have this. Now I've multiplied n by a number, so I'm just going to divide both sides by that number. So n is equal to, now I can just put all of this into my calculator. So put all of that into my calculator to figure out what my n value is. And I get 12.86. Now, let's go back here and just see how they wanted us to round it. They just want to know how many years it's going to take. Okay. So if I look at this here, I'm going to say 12.9, but I'm going to round it's in between 12 years and 13 years. So I'm going to say that n is equal to 13 years. Because I haven't reached that at 12 years, I need to go the full 13. Okay, so that's how you should have solved it, by separating them out. What I want to look at is a better way of doing this. Okay, so whenever I have just one power, I would never take the log of both sides. I save that method for when I absolutely have to use it, because it's really time consuming. So what I'm going to do is isolate my power and use bay. So dividing both sides by 4,830. I get this. So the first thing that I want to do is put my fraction in lowest terms. So 800 over 483. So I'm going to have 800 over 483 equals 1.04 to the n. And then I'm just going to switch it to log form. So base of the answer equals the exponent. And then I can just put it in the calculator, see if I get the same answer. And I do get the same answer. So 13, again, rounding it to 13. This would be much easier here. So anytime you have just one power, I want you to switch to log form, so much easier. Okay, for the last part of this lesson, I want to look at half-life and doubling time. So half-life is the time it takes an object to become half of its original value. So what we're going to do is take that formula that we've been using and apply it to half-life. So the formula is going to look a little different. So remember we started with this, y equals a times b to the x. So y we're now calling a, but it behaves the same way. It's the final amount. Your initial value of a is called a sub 0, which just means the amount at 0, whatever the unit of time is, 0 hours, 0 days. So it's your initial amount. So that's still the same. The base, this time here, it's always going to be half because it's half-life. Now, what the difference between these two formulas is the exponent. T over h is the same as x. Now the reason that we have a fraction there is because half-life is how many times it's cutting in half. So let's say my half-life was 4 days. So that means it takes 4 days to cut my quantity in half. If I want to know how much there is at, say, 2 days, my exponent wouldn't be 2, because that would imply I've gone through the half-life process twice. It would actually be 2 divided by 4. I would only have half of that amount. So it would be, the exponent here is always your unit of time divided by your half-life. So let's try a question using this formula. So we have the accident, the nuclear accident at Chernobyl, and we're looking at how much radioactive iodine is remaining. So the half-life of radioactive iodine is 8.1 days, which is your half-life here. So to determine the number of days, we don't know that, it took for the level of radiation to reduce from 100 units to just 2. Okay, so applying that into our formula, 2 equals 100 times 1/2 to the t over h. So I only have one power. We're not going to log both sides. We're going to use Bay. So I'm going to divide both sides by 100. And I get 1 over 50 equals 1/2 to the t over 8.1. And now I'm just going to use Bay. So base of the answer equals the exponent. Okay, so this log base 1/2 of 1 over 50, it's just a number. So I can put that into my calculator to figure out what the number is. Okay, so this is like 5.64, etc., equals 2t, over 8.1. And then what I would do is I would just multiply both sides by 8.1 to get rid of my fraction. So doing that, multiplying this side as well, keep that answer on your calculator and then just multiply both sides by 8.1 and you're going to get your answer there. Okay, so 45.7. Let's just go back up, see how we're supposed to round that. It says to the nearest day. So the day that's closest to is the 46th day. So that's how you would do half-life. So I just want to look at a doubling time example now. Okay, so doubling time, same kind of an idea as half-life. A patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells, so that's my initial amount. 24 hours later, that's my time, the sample was recounted and was found to have 8,012 cells. That's my end amount. Find the doubling time it takes the bacteria to double to the nearest 1/10 of an hour. Okay, so let's plug everything we know into the formula. 8,012 equals 387 multiplied by 2 to the 24 over d. Okay, so I only have one power, so I'm going to isolate the one power and then log both sides. Take the log, sorry, switch it to log form. Don't take the log of both sides is what I was trying to spit out. Okay, so 8,012 over 387 equals 2 to the 24 over d. So, because I only have one log, I'm going to use bay. So, base answer equals exponent. Okay, so this log here is just a number, so I can put it into my calculator to figure out what that number is. So it's 4.37, etc. equals 24 over d. Okay, so now what I want to do is isolate my variables. So I'm going to multiply both sides by d. Gone. So I have d multiplied by 4.37, etc. equals 24. So to get d by itself, I'm going to divide by 4.37, etc. to both sides. Let's try that again. Okay, there we go. So do that to both sides, and then we're going to get what d is. Okay, so I can just plug that into my calculator and get what the answer is. So 24 divided by 4.37, etc. 5.489, and they said to round it to the nearest tenth. So that would be 5.5 hours. Okay, so the key to these things is just like stating the formula, plugging in everything that you know, solving for what you don't. So to summarize, if we're dealing with growth, the base is greater than 1, 100% plus the growth rate. If I have doubling time, that's also a growth example because the base is 2. If I have decay, that's when the base is less than 1. That's 100% minus the decay rate. So half-life is an example of decay because the base is a half. So for half-life and doubling time, remember your base is always either a half or 2 respectively. The exponent is always time in general divided by the half-life time or the doubling time. I like this equation. Get a half-life instead of a life. And this is actually a half-life formula. So I want you guys to do assignment questions number 1 to 12. I hope this video helped, and I'll see you for the next one.